Can you hear me? Okay, let's give it another minute or two for people to copy over. I apologize for the issues. Like I said, this is the first like YouTube stream, so hopefully it goes well. Hopefully it saves it, but we'll just have to see. Might have to do this later for another group if that's the case. I can try. Yeah, just don't know. So how this is going to work is I will do my best to pop over into chat like every few slides or so to see what people are saying, or if you have questions or anything like that. So yeah, actually, let me copy this link more directly. I couldn't find that link to start with. Yeah, so I apologize. I have a feeling the stream quality won't be all that great. We'll do my best. I mean, I mainly be working off some PowerPoint slides, and hopefully since it's a PowerPoint slide, there's not like a lot of animation and things like that. So hopefully you'll get a decent stream. Maybe not. My home internet isn't the greatest, and as you guys might be able to see, I don't know what the problem is. Although let me check something real quick. I'm gonna stop streaming for a second. Okay, I tried updating my streaming settings. Do you guys notice any difference? Or I'm hoping you can still hear me. All right, good. Yeah, sorry. Again, first time streaming, I usually just do a Google Hangout, so there'll be a little bit of a delay. It looks like there's probably a couple seconds of latency on my end, but like I said, so we're gonna go through. So let's just get this started then. So we're gonna do a machine learning kind of tutorial today, and really, it's gonna be focused on really just the bare essentials. So there's not gonna be a whole lot of deep dive, but since most of you probably machine learning is a very new concept, this is usually what I do at the start of the semester to get at least people up to basics with some familiarity of some of the terms and terminology, the terminology that not only is used in the community, but that I'll use throughout the entire semester, so that when I have questions about your projects, I'll want to make sure that we'll want to make sure that we're talking the same language, so that when I ask you a question, you'll know what I mean, and you'll have an answer ready, or you'll know what area to investigate. Okay. Let's see if this will open for me. Come on. That doesn't look right. Come on, Microsoft. It's frustrating. I just had this open full screen too, but it's like from Dropbox. Oh, that's good. Good UI, their buttons are all hidden. Okay, and I want to check real quick since I know where that is. You guys can see my PowerPoint deck? All right, great. Okay, so machine learning. So this was actually, I taught the data structures undergraduate class, and this was like kind of a fun topic for the very end of the semester. So it's a little geared towards data structures, but I usually go through it through the perspective of a senior design capstone student and explain things and focus on things more specifically for that. So to get started, this is a bit of a generalization, but it holds true really for what I think is all of the projects that we have this semester. But really there are two main categories of machine learning algorithms, and they're called unsupervised and supervised learning. They're semi-supervised and reinforcement learning, some other like fancy ones, but for the most part, those have different problems that they're trying to solve. But these are like the two major ones that you see in industry and what most of your projects would probably be focused on. And so we're going to go through each one and talk a little bit about kind of what their role and what their purpose is. The first is unsupervised. So these are problems where you're trying to find hidden structured in what's known as unlabeled data. And we'll talk about what labeled and unlabeled data is. And supervised learning is analyzing labeled data. So right there you see a key difference between unsupervised and supervised learning is labeled versus unlabeled data. But supervised learning, analyzing this labeled data and producing an inferred function which can be used for mapping new examples. And so to just really broad stroke it, unsupervised learning oftentimes is used for like data discovery and learning about some new data set and just kind of doing data exploration. Where supervised learning is usually we're talking about things in the predictive analytics space. So that's usually this like inference function that you're trying to figure out is you're trying to make some sort of prediction. Not necessarily into the future like a forecast, that's kind of something related, but not quite what this is. But we can think about these in broader terms, and the terms is just a prediction. So let's start out with a key concept, and that is this concept of labeled versus unlabeled data. So data is usually represented as a multidimensional point. You'll read about this also being known as a feature vector. Each feature, so you can think about this as like rows in a table. Just like rows in a table, we might have two attributes, height and weight. Each one of these rows, you can think about it as one point, right? So height might be X and weight might be Y. But this extrapolates, right, to Z and A and B. There's no need, it doesn't need to be a two-dimensional point. It can just be some n-dimensional vector of attributes. These attributes are often called features. So height would be a feature and weight would be a feature of your data. And again, each one of these rows could be then called a feature vector. So we're used to seeing a lot of data like this. In addition, this was to make the point that that you can have more than two data points, more than just an X and a Y. You can have a Z or whatever. And to make the point that there's nothing to say that one of your features, one of your columns, one of your attributes, it doesn't have to be like numeric. It can be categorical, it can be strings, it can be other things. And depending on the algorithm that you're looking at, certain algorithms can handle different data differently. But in general, you're trying to boil these down into, you're trying to transform your data into feature vectors. And that's a whole science in and of itself. We can talk about that as the class progresses. But I don't care if you have text data, if you're like looking at web data like HTML, stock market prices, weather data. I don't really care what it is. More than likely what you do is you're going to take that raw data and you need to transform it somehow into feature vectors. Determining what those features are and how many they should have, that's part of the research project that we're going to have to do. And like I said, I'll be happy to work with you guys individually or as teams or in a broader sense if there's commonalities to help figure out what some of these challenges are. Okay, so talking about labeled versus unlabeled data. So let's take that table of data that we had and let's actually plot it. We kind of talked about it. Well, it can be an X and a Y position. And so we can plot this out. just like this, we might see some scatter plot if we were to do a scatter plot visualization of it. And I'll make the point that right away we're starting to use some unsupervised approaches in doing data discovery. So just plotting data is a great way to start to get a feel for the shape of the data and clusters and groups within that data set that you might not see otherwise. It's pretty hard just to look at a table of numbers and like infer correlation by itself. Like that's really difficult to see, but we're very visual learners, and we can oftentimes just inspect those sort of things by plotting things out in scatter plots or in other data visualizations. I'm a huge proponent of data visualizations, especially early on in the projects when we're just given a bunch of data and we're just trying to learn about it. We're just trying to figure it out and understand it. Sometimes these visualizations can help tremendously when we kind of plot out our feature vectors. So oftentimes, though, you might just be handed a lump of data and been told, just tell me something interesting about this. You know, find things that are correlated, or what are my outliers? Is there any like anomalies in this data that you might see? These are all questions that are suited for unsupervised learning techniques, which we'll talk about in a second. But really, it comes down to this being unlabeled data. There is no real like labels on what these things are. However, we could add a label to it, which really, by adding a label, all I'm saying is that we're identifying one of the features in our feature vector, or one of our columns in our table, however you want to think about it, as our label or our outcome. You'll hear those two terms used a lot. So in this case, maybe we're predicting male versus female. This might be some sort of animal, I don't know, a kangaroo or something like that. So by plotting this out, again, you can learn some interesting things. So maybe for this, whatever this is, a species of something, it looks like there's a correlation between height and weight, and it looks like the females tend to be shorter and weigh less than the males do, for example. So just like that, you find some interesting insights just by like plotting data out. And so it's only natural. Well, I guess I'll switch to that real quick. So a common data set, you're going to see this probably, and many of you have probably already seen this in your in your research, is this iris data set. So again, I want to stress that it just doesn't have to be 2 dimensions or 3 dimensions. You can have many of them. So in this case, we would say that this is looks like there are 5 columns or 5 features in this feature vector. And this was for measuring plants. So there was, I think, 3 species of plants, in particular flower and iris flower, which is a picture of it. And scientists went out into the wild and they recorded different measurements about the plant. The length of the sepal, which is some measurement of one of the petals, the width of it, height, weight, those sort of things. And then they identified what species it is. So this is kind of a cool data visualization that if we were to do the same trick that we did with the height and weight before, this is to show that you can plot more than 2 things in a scatter plot. This is called a scatter plot grid, where every one of these cells is the combination of 2 of them. So for example, this cell here that I'm highlighting would be, the y-axis would be the sepal dot length, basically the length of the sepal, and the x would be the sepal dot width. And so you can quickly see like a lot of slices of your data, which is usually a really effective way to do it. And it's color-coded based on the species. I can't remember which one's red and green and blue. But you can kind of see, this is interesting. So again, this is like an unsupervised technique of just plotting it and like finding something interesting. It looks like this red species is fairly separated from the other 2, right? It's like us as humans could quickly see this and say like, oh, this is, there's some fairly strong characteristic differences for our reds. Our blues and our greens, they're obviously more jammed together than the reds were, but at the same time, it looks like at least on some of the dimensions, they're pretty separable. We can find kind of divisions between them. It's not just a complete, like, if it was just complete noise and it was just all reds and greens and blues mixed together, that might be really difficult to get anything meaningful out of it. But we could say, for example, that our greens, for example, the Verisa color or whatever, it looks like their petal lengths tend to be smaller than the blue Virginica ones. So again, I'm urging you to explore your data first and foremost. And in doing that, you're going to be asking yourself some unsupervised learning questions. And so these questions might come in the form of, do there appear to be distinct groups or clusters within my data set? Or what do the distribution, the means, standard deviations, medians along each dimension look like? Maybe plot out, break out your statistics textbook and plot out distributions of some of these. Maybe for some of the variables, they have huge standard deviations and it's all over the place, but other ones are very narrow and they don't deviate a whole lot. Other questions, are there certain attributes, dimensions, features more spread out than others? That goes along the same lines of this like probability distribution in the beginning. And are some dimensions similar to each other? And I put similar in quotes because those could be correlated. It could be causation. It could be a lot of different things. But oftentimes you want to look to see, are some of your dimensions, some of your features or your attributes, are they correlated or similar to each other? So if we pop back here, for example, we see that there's a pretty strong correlation, it looks like, between the petal length and the petal width, which tends to make sense. You would think that as a petal gets bigger, it needs to get wider and longer kind of together at once, where maybe some of these other ones don't seem as strongly correlated. So the sepal length and width, not necessarily the case, but maybe correlated within things. Anyways, so the bottom line is these are all unsupervised learning techniques. So there's a couple common things. I mean, mainly when you look at like unsupervised algorithms, they fall under a lot of them fall under either just straight up statistics. So finding averages, standard deviations, that sort of stuff should be pretty straightforward for you all to figure out. Any spreadsheet tool or Python or R or whatever should be able to chew through your data and give you that sort of stuff really, really easily. And then there's clustering algorithms. So clustering algorithms try to do what our minds can or our eyesight can intuitively do. So us as humans, we're really good at visual learning. We might see this scatter plot, and just our eyesight alone tends to kind of draw circles around things and see, oh, it looks like maybe there's 4 groupings. Obviously there's some outliers here and there, but in general it looks kind of like there's 4-ish clusters. And so there's a number of clustering algorithms. R and a lot of other ones have, oops. Let's see if I can pull up so this was like a famous one called the K-means algorithm. For your purposes, a lot of times you can just treat these kind of as black box algorithms. So you can feed your data into like a K-means, and basically the output, as we'll see, as I'm sure this is just trickling in, this is a GIF that apparently is loading really slow. This is kind of the algorithm working in action. And I'll let it play for a little while longer, but the main idea is that it kind of iteratively tries to find clusters and groupings of your data points, so then at the end of it, you can kind of have these things labeled into distinct sets. And as you can see here, as it's starting to converge, this kind of intuitively found kind of the groupings that we probably could see with our eyes from the beginning. So it's really like an algorithmic way to try to discover these things. And imagine that instead of just 2 dimensions, you have n dimensions, right? So you're trying to find these clusters in not 2-dimensional space or 3-dimensional, but it could be n-dimensional space, a high level of dimensionality. And so you can't just visually look at things. It's just too much data to process visually. Just gonna pop. Okay, so we're still running. Okay. So that's a little bit of unsupervised learning. There's also things to do with hierarchical clustering. I won't necessarily get into that, but just know that there's many ways to skin the cat. There's many ways to try to answer this question of, is my data grouped into some sort of form, or is it just pure random noise? If you were to run some of these algorithms in just pure like noise, you just throw like random dots on into an X and Y grid, they probably won't do a very good job because there is no structure behind them, right? There is no underlying meaning, it's just noise. But these are really trying to find the meaning within a vast data set and try to take that noise out of it. So while unsupervised learning is fantastic and has a number of uses, a lot of times, especially in our class and in industry, you're going to be getting questions that are more of the fall into the supervised learning category. And really these come down to what class label value should a new unlabeled point have. So let me break that down a little bit because there is some terminology there. So let's take a look at our data set for our iris flowers. Remember that this had 5 features. Looked like 4 were numerical, 1 was categorical probably. This is just a text string, but there's 3 categories to it. So a really natural thing that you might ask is, you know, I'm a researcher, I'm a Boy Scout maybe, I am going into the wilderness and I find one of these flowers, it's an iris flower. I just can't pick the species though. I'm not that good. But I have a ruler and I know how to measure 4 of my features. A really common question to ask then would be, based on these 4 features, what is the most likely species? That is what would be known as a supervised question, or it's a supervised problem. That's how we would treat this. So the idea is that based on what we've seen before, which would what we would call a training set. So if you trained, you know, hypothetically, if you could train a Boy Scout to learn these relationships between these numbers and these species, then you could test them or give them a new example and leave off one of the features, and it would be able to kind of fill in that blank with high probability. Or at least that's the goal, is to get as high a probability as we can get. And so this is really the foundation of a supervised learning question. So if you have questions of this format, that would be supervised learning. And in this case, I'll mention that we would call this feature of species the label of the data. And we'd call it the label because that's what we're trying to predict in the end. That's the final label, that's the value, or another way you might hear it called is it's the class of the data. This is called a classification problem a lot of times. So if you're doing research, you probably have run into that. So this would be considered a classification problem. With very minor changes, these sort of problems, you could imagine that these 4 numbers, for example, are the previous 4 days stock market price for a certain stock. And you're trying to predict what tomorrow might be. By looking at tons of data from the past, maybe we can predict with some sort of accuracy what tomorrow's might be. Or I'm trying to think of some of the other problems that we have in the class this semester. Maybe these are various word counts on a web page. So the number of times you see the word Math 101 or something like that. And you might want to be predicting, is this the course catalog page for a university or something like that? I'm trying to think of like some of the web scraping problems that we might have this semester. So the first step for almost any data problem, any sort of like predictive problem like this, is transforming your data into a feature vector. I can't iterate that enough. And that takes a lot of thought, and it's going to take us a lot of research, and we're going to have to play around with things. But at the end of the day, then, we need to identify also, what are we trying to predict? What is the outcome that we're interested in? So this would be like and I wanted to point out here, I guess I got a few slides on it. Like I mentioned, it doesn't have to just be like a categorical variable or some text string. You can also predict numbers with various techniques. So I'm kind of wiping my hands over how you would do this, but just know that they fall under this category. So you can predict numbers or categories or outcomes a number of different ways. One of the easiest ways, so let me just talk about maybe the very easiest way to predict. So let's say that we had our original heights and weights, and we plotted them out, and we had males and females, and let's say that we wanted to make male or female, we wanted to make that our class or our category or our label, and we got a new point. So we found some data, but unfortunately it didn't have it labeled being male or female. So we could plot that out. So we found the new data points right here, and it's very natural to ask ourselves, what is this? Is this a male or a female, whatever that might mean? The easiest way to do it, probably, or the most the most simplistic, I'll say, is using something that's known as like the k nearest neighbor. So in the k nearest neighbor, typically you pick a k that's an odd number, probably like 1 or 3 or 5, and you simply look up the closest neighbors to our new point. So the 5 closest points to our unidentified one or unlabeled one. And then you just use a voting mechanism. And you say which class, female or male, has the most votes or the most frequent. So in this case, female looks like it has 3 of the 5 and male only has 2. So we would just say we're going to predict that this dot is female. Now, who's to say that's a good decision or a bad decision? It might make sense for a lot of applications. Other applications, this k-nearest neighbor approach doesn't necessarily work the best. But there are lots of different ways to do this. Another different way is something called a decision tree. So decision trees can be built algorithmically, and they're kind of these cool things because they're really interpretable. They're a big fan. They have a lot of uses actually in the in industry because of their interpretability. They're not just like some black box. When they're done, they have kind of these like rules. So how you can kind of read one of these outcomes is that we would take in a new, let's say we had a reading for a new flower. This was like a Boy Scout, right? He recorded some things. He can look up, he would take the petal length as the first reading. These kind of move top to bottom. You'd say is the petal length left center equal to 2.6. In that case, we're going to say that this was this species. Otherwise, if it's greater than 2.6, then we need to do another evaluation. We need to next check the petal length. And so you kind of, it builds this like if-then kind of tree of logic that breaks down, and that each one of the leaf nodes is a final classification or a final label. And usually these labels are probabilistic. We could talk about that for a long, long time. But usually none of this is like with 100% certainty. If it is with 100% certainty, we probably are doing something wrong, to be quite frank. Okay, so that was kind of a little bit of warm up on supervised learning. I'm going to pause here for questions. There are no questions. That seems hard to believe. Okay, so I'll take them one at a time. So the top part of the tree, is that the most deterministic feature? That's a really good question. That actually will vary. Oops. That'll vary depending on the algorithm that's used just to build it. In some case, these algorithms try to split things. They try to split things to kind of build even trees. You know how you have like balanced binary search trees? And other times they try to kind of quickly prune away or answer questions like the easiest first. So if there is like a really deterministic feature, it'll pick that one first and try to like crop away kind of the easy answers. And then the deeper you go, it gets like harder, and you kind of think of that as like harder and harder and more ambiguous and more ambiguous. That's a little bit of a detail into a decision tree. There's a few different types of them that you can, lots of different types that you can build. So I can't answer with certainty, but I would say most of the time, yes. It's usually like with a C5 tree, it tries to pick the features that are most deterministic. Okay, what are some common mistakes you see in supervised learning projects? That's a good question as well. The main thing I would say is students or projects in general, really not just students, we tend to like to shoot in the dark and we tend to run forward without really identifying what it is that we're trying to improve. So this is an excellent segue because this is, I think, the first thing that we need to identify with any of our projects is, well, I should say maybe it's the second thing. The first thing is, what are we trying to predict in a supervised learning project? What is our outcome that we are trying to evaluate for? Is it some sort of number? Like, for example, this, like I'll take stock market prices, since that seems to be usually a common one and a proper one, or a common one and a typical one. So it's easy to say that, oh, the intention of our project is to use some new data source to predict the stock market. But what does that mean? Does that mean that you're trying to predict the S&P 500? Are you trying to predict a particular stock? Are you trying to predict a particular stock for tomorrow, or the average for the upcoming week, or an average for the upcoming month? Are you trying to predict the high for tomorrow or the low for tomorrow? Are you just trying to predict, is the stock price going to go up tomorrow? Or are you just trying to predict, is the stock price going to go down tomorrow? So the point is that identifying what it is that you're really trying to predict, all those things might have different outcomes and different ways that you want to go with your research. But that needs to be identified up front. That'd be one of these like requirements that I would sit down with your client and make sure is crystal clear. Or if your client doesn't have a preference, maybe they have some higher level goal, make sure you discuss it with your team, your TAs, with us, to make sure you know exactly what it is that you're trying to predict. I know like the house team is taking a look at images. So they have a bunch of image data and they were trying to predict a couple different things. They're trying to predict areas of their images that had like cancer cells, or they were trying to take a look at an entire image and their outcome was sick or healthy, like just good or bad. All those sort of things have vastly different performance measurements. And when I say performance measurements, I mean like accuracy measure. How do you determine if what you're doing is any good, right? You can come to me and say, oh yeah, look, this thing is, it's doing great. It seems to be good. I need numerical numbers to determine that. So it starts with determining what you're actually trying to predict. After that is then about getting a good baseline measurement of how well you can make a prediction, because there's so many factors that are going to go into it. The most important factor, well, I should say probably two of the most important factors are, one are the features. So once you have a prediction that you know that you want to do, so let's say that we want to just predict if the Microsoft stock will go up tomorrow. Up or down, I should say it that way, like an up or a down. That's all I want to do is determine if Microsoft stock will go up or down tomorrow. Then I have to determine what features go into that prediction. What features do I want to use? I could use the stock market price yesterday. I could use the stock market price from 2 days ago, from 3 days ago, from 4 days ago. Maybe the overall S&P 500 scores from those 4 days. Maybe I want to also include competitors' prices, like what were Apple's prices from those past 4 days. It could go on and on and on, right? I could keep on adding more and more features. I could add how many tweets does President Trump mention Microsoft in the past 3 months? It could just, this idea of then adding the features into it will make a ginormous impact on how well your predictions work. But that brings me to the next topic, and that is, what does it mean to have a good predictor? What does it mean to have a good machine learning algorithm that can make really good predictions? And so to demonstrate that, I want to talk a little bit about a few things, and you guys will have to jot down a couple notes. Because we have a couple pet peeves in the class that I want to discuss. Because I want to get us off on the right foot, because if we don't, then oftentimes we waste a lot of our time and our energy. So I want to start off by let's just say that we have some hypothetical data set. let's see, I have a cat that will not seem to leave me alone tonight. So let's say cat height weight data set. Oh, and let's say that we measure a bunch of cats' heights and weights, and then we also determine their gender. So let's just, these are all just going to be funny numbers, obviously. So let's say these are in inches. I don't know what an average cat is, so I'm just making some things up. Maybe a couple of these are kittens, so they're really small. Oh, whoops. It doesn't matter. Wait, yeah, that's a really big cat. I don't know. Yeah, these are inches, something like that. Oop. Doesn't matter. And let's say that we just had some genders. Okay. So as I mentioned, so this is my data set. Again, this would be considered what we would call the training set. So any data problem that we have, we need to have data to do it. Anecdotal evidence doesn't fly, obviously, in this class. We're trying to put some rigor behind it. So if it was like stock market, we would need to kind of go and find an API that lets us access stock market prices for some history. Or if it's doctor imaging, like x-ray imaging, we need to somehow find some open source or some freely available data set with images of lungs or hearts or whatever we're trying to target. If it's web scraping, this is something where oftentimes we have to go get our own data sets. Getting the data set oftentimes is one of the biggest challenges. So you might have to write code that goes and scrapes websites for various attributes and then use it to build out some feature vector to then be able to predict whatever it is that you're trying to predict in the long run. But nonetheless, so once we have our data set, which this would be what we would consider a training set, then let's say that we have something new in here. We just got a new one, 7, and we don't know what this is. So what would we end up doing? We would end up taking this information, we would build a decision tree or use k-nearest neighbor or some other classification algorithm, which I can talk about. There's tons of them, neural networks, whatever it is that you might want to use. And we would train those systems on this training set. And then we would show it a new data element, an unlabeled one, and make a prediction. And so we need a way to determine if when we did our training, if we did a good job or not. We just don't know at the time of training. So the most common approach stem from what's known as a confusion matrix. And let's start though, like with the basics. So one thing that you can do, instead of calling this gender, I'm going to call this actual gender. And over here, I'm going to call this predicted gender. So what you could do to try to determine if your classifier or your predictor is any good is what's known as leave one out validation. And so the basic idea is that I do that same process where I take everything in my training set except for one row. So just leave one row out and train an entire decision tree or k-nearest neighbor or whatever it is, random forest, neural network, whatever it is, on the remaining data. But the key is you cannot show it whatever it is that you're trying to predict. So in this case, let's say that I was trying to predict this last row, or this first row, I'm sorry. So I train my entire neural network with everything else, and then I feed my decision tree these two values, width and height. I feed my predictor. I'm going to start using that more generically. I feed my predictor the width and the height, and it predicts a gender. Maybe it predicts male. I can then compare it to the actual, and fantastic. It matched up perfectly. Then what I can do is the same process, except this time I'm going to leave out just the second example. I'll include everything else. Oops. everything else except the middle one, or the second one. And then, so I'll do the whole training. I'll build a whole new decision tree from scratch, whole new neural network, whatever it is, a whole new predictor. And then I'll feed it this and make another prediction. Crud. This time it didn't do well. But the idea is that we're going to repeat this process over and over and over again. And at the end, we'll have two columns that look roughly like this, an actual and a predicted. Excuse me. So with these, we can generate a ton of different pieces of information. And this is where the term that you can Google search, confusion matrix, comes from. It all starts, though, with identifying, and let's just make this brutally clear up front. I do not like accuracy as a way to measure how well your predictor works. So what could we do? We could, and it makes complete sense. The first thing that we would probably do, we would just add up the number of corrects. So we'd say, oh, this one is correct, and that one is wrong, and that one is right, and right, and right, and right. And that one's wrong, and that's right, and that's right. And we can add this up, and that comes out to 7, and there was 7 out of 9. Oh, come on. You'd come to, really? I don't know why I wasn't working. You'd come to me and you'd say, Dr. Sam, fantastic. We're able to predict things with 77.7% accuracy. Isn't that fantastic? And I would say, no, that sounds terrible. Or I would say, probably more politically, I would say, I'm not sure. I'd have to see your data set. So the problem with an accuracy metric is that it's very subjective to the original data set that you have. So let's say that hypothetically, our data set here was almost entirely male. There's 2 females in the bunch. And your predictor came up with something like this. So again, there's 2 mismatches out of 9. So again, we'd have like 77% accurate. And you would be thinking, oh man, that's so great. I'm 77% accurate. But in reality, I, myself, as a professor, could have come up with an equally as good predictor by just always guessing M. If I were to just always guess male, given this data set, would it not also be 77% accurate? I would get my 2 mismatches, but the majority of my training set's male. So why don't I just always guess male? Obviously, the predictor that I have isn't very accurate. It doesn't really do much. It just always guesses one thing. Like, what good is that in the real world? It's not. So we need better ways to determine if what we are predicting is good, if we're making good predictions. I'm trying to use good and not say accurate, because accurate comes with that term accuracy, which is a very technical and specific term. I'm going to quick jump over here. Okay. So I'm going to keep going, but then I'll come back for questions. So if we search confusion matrix in Google, which is our favorite, there's tons of good things. But the most important part of this is this idea of plotting out your actuals versus your predicteds. So that's what I'm going to do. I'm going to come here and I'm going to plot out actual, I'm sorry, natural male, natural female, predicted male, predicted female. And I'm just going to fill these in. So let's fill these in with what I have over here. So it looks like there are, 1, 2, 3, 4, 5, 6 here. And it looks like actual females, looks like there was one there. For this one, there was an actual female, but it predicted male. One there. Here was an actual male, and predicted female. I did this. This is much more meaningful to a data analyst or to a data scientist. This tells a much clearer picture about how well your model is performing. What you want is you want your predictor to be along the diagonal. It wants the actuals and predicteds to be the same. If, for example, I was only predicting males, remember I kind of came up with that example, or if I just made a dumb predictor that just constantly guessed this, what would we see? We would see in the actual section, it always predicting it. But here we would have something like, oh, wait, I'm sorry, I flipped that. We'd have something like this. And just by glancing at something like this, it'd be really obvious to any sort of data analyst that my predictor is not, first of all, it's not predicting female, and more importantly, it's just always predicting male even when there's a female. So you can get like some deeper insights by looking at what's known as this confusion matrix. And going along with this, there's all sorts of other metrics, true positives, true negatives, false positives, false negatives. These go by a couple different names. I'm not going to go into the details. But basically, from these numbers, you can derive other numbers. Typically, you see, and I'll leave this to you to kind of look into, the true positive rate and false positive rate are very popular metrics to try to improve. Specificity and provision are also very popular. If you guys get far enough, we can talk about F-scores and ROC curves. But for now, I think I'd like us just to start with some of these and get familiar with this terminology. They go by a couple different names: error rate, sensitivity, recalls. These are the fundamentals, though, that any data scientist, any data analyst will understand and will appreciate in your data analysis. Just using accuracy, like I said, is usually not very good. The only exception is really if you can isolate these, if you can guarantee me that your data set has like an equal number of classes, both in whatever direction or however it is, they're uniformly distributed, then maybe accuracy starts to be more meaningful. But as a rule of thumb, I try to avoid it as much as I can, and I just don't see it used very often. So that's a little bit about first of all, how would you evaluate the performance of your predictors, and both from like an implementation, or not necessarily implementation, but like this strategy of leaving out data and then making a training with the rest of your data, and then predicting with the data that you left out, and then this is how you compare your actual and predicted. So I'm going to stress one more time that never in any circumstance should you ever report some sort of number, accuracy, specificity, confusion matrix, anything like that, if all you're doing is you're building a model, building a predictive model on an entire data set, and then just showing that model something that it's quote unquote already seen before. So if you train a model on everything and then I feed it this 2024, I better predict a male. Or I would hope I would predict a male. Like maybe it's not necessarily guaranteed, but it would have much better option, much better chance. But it's disingenuous. It's like the equivalent of showing students the answers to the test and then having them take the exact same test. You would hope that it would do a really good job. But it doesn't demonstrate how well that students actually learned, how they could apply their knowledge elsewhere. So it's important that we follow that same principle, that we show when we're building our predictive models, that we show them some data and then predict other data that they've never seen before. So you got to make sure that you do that. Otherwise, these numbers will come out too good and we'll be skeptical in class, and you'll say, oh, I have 100% accuracy and it's never missed any of these things. And then we'll scratch our heads and we'll dig through your code. And more than likely, it's because we have some sort of mistake like that. We see that very, very frequently. So be very careful when we're doing this sort of stuff. Okay, do we have any questions? I know it's getting late, and I'm pretty much at my time limit. Okay. Are there different types of models per data type or media type, strings, numbers, images? I'm going to cautiously say no. I'm sorry, there are different models for each data type. It's not per data type. So at the end of the day, it really is about getting your data into some sort of grid, some sort of table of numbers. Even images can be thought of as, because an image, what is an image? An image is just a two-dimensional matrix of pixels. Those pixels have RGB values. Those RGB values are numbers. So oftentimes, you might be transforming your image data into something like this, where the first pixel is a full red, and the second pixel is a full green. Oops. And you want to predict, is this a male or a female? Like, I don't know. And so you would feed these things potentially tens of thousands of features. And there's better ways to do this. You wouldn't use k-nearest neighbor or something like that. But the main idea I do want to stress is that it all does start with representing your data, whether it's sound waves, images, text strings, whatever it might be, as features. That being said, there are a large number, and I'm just going to, I usually like to take this part, it's a little bit more personal because every project is going to have specific requirements that probably lend itself to various data models. So for example, for images, we probably would use like deep learning nets, which are a special type of classification net. It's kind of like a special type of neural network. For stock market prediction, we'll probably do something with like regression, for example. So each one's a little different, but they generally are set up the same way. So let's look at Python's scikit-learn, which is the de facto library for Python. For R, you probably use Caret or something like that. But let's just start with this one, because I do want to just show a little bit of this. So notice that when you go to scikit-learn and you go straight to supervised learning, again, this is a very common term in the industry, so now you know what it is. Remember, this is for when we're making predictive models. So let's take a look at, nearest neighbor. So you can read all about it. They probably do a fantastic job with how it works. This one's doing some pretty cool stuff with nearest neighbor regressions. You can see they're using images for this, so there you go. There's a lot more details about implementation of how these things actually get built. I was going to see if I can find like a code snippet. Give me 1 second. K-nearest neighbor classifier. Okay, so I don't really care if you're using Python or if you're using R or whatever it might be. Usually the setup's the same sort of way. Usually what it is there's a method called fit, or maybe it's called train, maybe it's called teach, but this is the part where you build up, you initialize whatever it is, a decision tree, a k-nearest neighbor classifier, a neural network, a random forest. There's tons of different ones, and just to reiterate, like if we just look at scikit, for example, we go to, this is their supervised learning. All of these bullet points, for the most part, I don't know, it doesn't look like all of them, but a lot of them are these sort of algorithms that can, they're their own models. So right here, tree algorithms. So these are all decision trees. Each one's slightly different. Each one kind of has pros and cons. And so it's going to be up to us to try to figure out which ones are best. Thankfully, a lot of them are set up the same way. You simply just pass in your data set to this fit method, and then you can take the output once it's been fit and call predict on it. So this is the equivalent of doing that process that I talked about here, where we're taking some data set and we'd call fit on it, and then we would take something it hasn't seen before and call predict. A lot of these libraries actually have they have built-in ways to build the confusion matrices and do all those sorts of things for you, like out of the box. But that's generally what I guess I'll just be. I mean, we can talk more individually about individual projects, but just know that there are a ton of different options out there for, you know, you might want to say like, what's better, decision trees or nearest neighbor approaches? Well, why don't you just try both? Try both and see which ones have better looking confusion matrices, have better specificity, have better true positive rates, false positive rates. There's trade-offs all over the place. And I do want to say, I'll mention this because I usually do, those trade-offs, oftentimes, the trade-offs could be coming from your client and they don't even know it yet. So one of the another motivation why accuracy is a poor way to measure this sort of stuff is, let's take a look at the healthcare system. Let's say that we have some new test on the market that that you go to the doctor's office and they do a test for you to see if you have some sort of disease. And obviously this test is going to make a probabilistic prediction. That actually might not be obvious to you, but almost no test is 100% foolproof. They swab your mouth and they send it away to some magic lab and it comes back some test result. Those things usually are probabilistic. There's usually not some like strong guarantee that they're always 100% accurate. Usually there's some sort of probability tied to that prediction, to that guess. And so oftentimes, so let's say instead of this is actual sick or actual healthy. And this is predicted sick and predicted healthy. So let's take a look at the confusion matrix for something like this. So let's say that you're actually sick and it predicted you sick. This is great, right? Very good. Awesome. Nailed it. What if you're actually sick and it predicted that you were healthy? That's probably pretty bad, right? Because the sickness will probably just get worse and worse and worse. And maybe if it's a bad enough disease, it might become too late. It might not be good. What about if you're actually healthy and it predicted you sick? Well, that's probably not great. You probably have to come back to the doctor. They'll probably have to run more tests. You might get on some other medication. But, you know, it's being like overly cautious. That might be a good thing. And if you're actually healthy and predicted healthy, obviously that's a good thing. So I just wanted to emphasize here that depending on your cases, like for example in the medical field, it might be a really bad thing if the disease is severe enough to predict healthy when you're actually sick. So you might want to look for your supervised training algorithms. You might want to be looking at building predictive models that really stay away from here. Because this is like, in that case, the worst scenario. I'll just spin it though real quick for you. Let's say that this was like the common cold, for example, right? Easily curable, really you just kind of got to wait it out. So in that case, if you're actually sick and it predicts that you're healthy, I mean, it's not the end of the world. The doc's going to send you home, say get plenty of rest, and it'll probably just clear itself up anyways. If you're actually healthy and predicted sick, then maybe the doctor like writes you a prescription and you got to get on some antibiotics. And in that case, maybe like for a really minor disease, that just stinks because it's just going to mean more cost to you, more cost to the healthcare system. So in case for like the common cold or something like that, you know, maybe you want to stay away from this area down here. So the point being, and I'm sorry, I kind of got off on quite a few different tangents here based on the initial question, but I did want to, again, emphasize how important these confusion matrices are. Depending on your data set and depending on the problem that you're trying to solve, you might be searching through some of these algorithms and tuning some of these things, support vector machines, ridge regression, GLMs, to have better confusion matrices. At the end of the day, that's really what we're looking for. And to start with, I would encourage all of you that are working, well, at least working with Python. If you're working with R, I can give you other recommendations. Just try some out. Like literally try them out and compare them. Luckily, a lot of these most popular languages like R and Python for this sort of stuff, if I just pick another one, for example, let's try gradient tree boosting classification. And I take a look at some example code, which I'm sure I can find somewhere. I didn't have any example code here, but I know for a fact that this is what it is. All of these follow the same pattern. They all have this like .fit method, and then they all have a predict method. So literally all you're swapping out is like a constructor for building the classifier in the first place. And there's various variables that go into those constructors. But you could just quickly try, I can't emphasize that enough, you can just quickly try out tons of different classifiers and just see like which ones seem to be working best for your data set. Every data set's different. Every data set's going to have pros and cons and strengths and weaknesses. And so oftentimes I just recommend students just try it out. I can't tell you like, oh, this is the best type of classifier out there, or oh, this is going to be perfect for classification. Oftentimes it's about just trying things out and seeing which ones work best. All right. A few more questions. Okay, next question. For a web scraping problem, you'd start by scraping a website for the data you need. You'd parse the data into a database, run a machine learning algorithm with that data from the DB. Every time a user wanted a result prediction on what's best for them. Potentially, yeah, I mean, this is a very, very general way of putting it. I mean, so it depends on what you need to do. Sometimes web scraping is just about literally scraping text and then like searching for things within that text. If certain keywords pop up or other things that might just be all that you're looking for. Certainly, yes, you could parse. So obviously this parse the data is extremely generalized. Parsing it for what? Certain HTML tags, certain keywords, all keywords, that could go a number of different ways. And then run a machine learning algorithm for the data in the DB every time a user. So yeah, I don't know if you do this like every time a user wants a result or prediction or result. So oftentimes, I will say oftentimes in the real world, these are like two-step problems. So the first thing is you find a model that works really well for your data. So you've analyzed a bunch of them. You found, oh, decision trees really kick butt. The confusion matrix looks great. My data for my data set. And now I need an end user to actually use this thing. They're going to be uploading fresh data, in real time. A lot of times building the models takes a long time, like not real time. Like you can't just click a button and then a microsecond later it returns a trained model. It does the whole training from scratch on the entire data set. Obviously I shouldn't say obviously, usually that's not realistic. But what you can do is maybe you just build that model once a month or once a week, maybe at midnight when there's no users on your system. You build a model using the latest and greatest data, and then for the whole next day or the whole next week or month or whatever, you just reuse that model. Because oftentimes the prediction part of it, you kind of saw there's like this training and then the predicting or the fitting and predicting. The fitting and training takes a long time, but the predicting is very quick. So usually you build these models, you cache them, and then when a user comes into your system, they enter their symptoms or they, punch in the latest stock market values or whatever it is, and then it just calls predict, and it calls that very, very fast. And so typically you would try to like cache the results of your model. You don't want to necessarily do that fit process in real time for an end user. Maybe for some admin or something like that. That's completely cool, but for end users, usually, yeah, I mean, these things could take minutes. Heck, for like image recognition and stuff like that, I have had models run for days on my machine using GPU computing and stuff like that. That's very common. So you want to make sure that, yeah, then I take the results of that model. The predictions are in milliseconds. Am I understanding correctly? So is web scraping in itself machine learning? I don't know about that. I think of web scraping as being a pre-processing step, to be quite honest. I mean, machine learning is kind of this broad term. Like, it gets thrown around a lot, in my opinion, probably more than it should. But usually when I do machine learning with web scraping, the web scraping is to build up my feature vector, and then I use machine learning to predict something else about it. I'll be honest, a lot of my web scraping problems don't even have that prediction part. They're just about scraping. Like, I need to find, I don't know, all the student GPAs in the class. If there's not like an API to do that, but I have access to a web portal, I might have to make like 20 clicks, or I could write like a web scraper that kind of simulates clicks and navigates around and scrapes all the GPAs that I have access to into a nice Excel document. That's a web scraping challenge. I don't know if I'd consider that machine learning personally. I personally probably wouldn't, but others might. So don't get too caught up in the terminology. Are there any other questions? So I'll be completely honest. I do not know enough about your projects yet to say how machine learning plugs into them. I really don't. I could see maybe hypothetically you scrape the web page, you build feature vectors with some terms that are on each web page, and then you're predicting, are you on the proper, like, I don't know if you're going to need to build like crawlers that like crawl over university websites, and you just don't know. Like, so one of the challenges is web scraping, especially if you're doing what's known as like web crawling, where you're just kind of like, you maybe know like, oh, MIT.com, but you don't know where their course catalog is or where their accreditation page is or something like that. And if the purpose of the project is to kind of automatically find that page, well, you're going to need to build a web crawler that kind of explores the various links starting with that homepage. Maybe it starts with MIT.com and then kind of simulates clicking on links to take itself to all the other various pages. But how do you know if you've landed on the page that you were looking for to begin with? That could be a machine learning prediction, right? So on each page, there's going to be different words. There's going to be different tags. Maybe that's your training set. Maybe you have like a number of the colleges. Maybe you have to look at 30 or 40 or 50 colleges and build a training set of what words existed on those accreditation pages for those websites. Then you could apply it more generally and go to new college websites that you've never been to and let a web crawler explore the web's page or the whole website, the entire website, not just the single page, but the entire website, clicking on links and going to different ones and using predictions to determine if the web crawler has landed on a page with the information that you're actually looking for. Otherwise, a human's going to have to go and look through all that data, which I don't think is the purpose of it. That being said, I really do not know the details of the AmSite projects yet. I'm super excited about it. Dr. Hashmi has been the one kind of taking lead on some of those. And you know, I just don't know yet. So I'm excited to go through the requirements gathering process and seeing what you guys, what the problem is that you're trying to solve. That's really where it starts. It's easy enough for all of our clients. They all respectfully, and you know, we love them for it. They all love to put like machine learning and predictive analytics down on like the student projects. We try to make sure that that's accurate to the best of our knowledge, but sometimes it's not necessarily the case. But I have a feeling there'll be some sort of application here. I just don't know enough about your projects yet. Recursive crawling, well, I don't know if it'd be recursive, but yes, let's just say yes. you probably don't want to do recursive because the internet's endless and you'll get a Stack Overflow. But I get your point. The answer is yes. Okay, any last questions? Of course, I'm happy to answer more and more questions in class and after class and the whole semester. Okay, would web crawling approach work on getting credentials from uploaded documents? I don't exactly know what you mean by that. If you're, yeah, I don't know. I don't know what you mean by that. Maybe you'll have to elaborate. I guess that's why we were confused, but you definitely cleared some things up. Okay, yeah, completely understandable. It's going to be confusing for a little bit, especially with the requirements gathering. Oftentimes after this, the students kind of have just kind of absorbed what I've said, and it really won't make sense until you start getting your hands on things, and all of a sudden the terminology will start to click more and more and more, and then we can have further discussions. But like I said, you know, I'm happy to chat anytime. I'm extremely passionate about this stuff. I work with it all the time. My PhD was in machine learning, among other things, and usually the projects turn out really, really well. Your TAs, a lot of them are very knowledgeable. Dr. Hashmi is really knowledgeable. We won't let you shoot yourself in the foot too much, but I just wanted to, today was really about giving you guys some pointers, giving you some terminology, and kind of giving you some gotchas to look out for. Okay, so with that, I'm going to call it. That's it. I'm going to try to figure a way to post this online. I have no idea though, so it didn't quite work the way I wanted to tonight, but we'll see. So please, and I'll try to send out, I'll send out that PowerPoint presentation as well that I had. Not that there was a lot of content in there, but anyways, I will see you guys tomorrow. Everybody have a good evening.